So today we're going to recap inverse functions. You may recall inverse functions from, back in term 1, wasn't it? We looked at inverse functions.
Right.
Remember, you got two sets of data, and if there's a one-to-one relationship between the sets, then we know both the relation and the inverse relation will end up being functions. So that's when the inverse relation, we call it inverse function. So basically, if that inverse relation satisfies the rules for a function, that's what we're really saying. So we know a function will either be one-to-one or many-to-one. Because we said for any input, maximum of one output to be a function. So if that function is one-to-one, that's when the inverse relation will be an inverse function, because it goes both ways, if you like. So it's one-to-one. So if you go backwards, you're also only going to get one result. And what we should see happening is the cancelling out, because functions and inverse functions should cancel. So the composite of the two should always give us x. How did we test for it? Well, the easiest way was the horizontal line test. Remember, so if we could draw a horizontal line and it cuts it maximum of once, then we know that yes, it will have an inverse function. The other way is if we swap the x and the y around and then make y the subject, we get something that's unique. We don't find ourselves saying something like plus or minus, where there might be two possibilities. Another fact about inverse functions, the inverse function of an odd function will always be odd. So it'll be an odd function as well. Whereas even functions, they won't have inverse functions. Because if you think about an even function, it has reflectional symmetry, so it will always fail the horizontal line test. Domain and range. So we know that if AB is a point on the original graph, then BA will be a point on the inverse, basically swapping the x and the y's around. So therefore, the domain and the range swap around. So the domain of the original function will be the range of the inverse function. And the range of the original function will be the domain of the inverse function. So we've been talking about exponentials, so let's have a look at y equals e to the power of x. And there it is. The domain of that, of course, is all real x, and the range is y is greater than 0. Now, our inverse function, we know for exponential, the inverse is the log. So we should find with our log function that the domain becomes greater than 0 and the range is all real y. And sure enough, if we were to draw it, and remember when we draw it, there are reflections in the line y equals x. There it is. And sure enough, it satisfies those domain and range conditions. When you think about it, most functions won't have inverses, because most functions aren't one-to-one. So we have to restrict the domain so we get a one-to-one function if we want to look at inverse. So we can make it invertible. What we basically want to do is restrict the domain so that piece of the domain is one-to-one. What you look for is this. It's just a piece of the graph which is always increasing or always decreasing. So if it never turns, then it'll satisfy that one-to-one that we need. So here's y equals x squared. And y equals x squared, of course, would fail the horizontal line test. Domain all real x, range is greater than or equal to 0. But no, it won't have an inverse. So I want to pick a piece of the parabola so that it's always increasing or always decreasing. Now there's two choices there I could make. Well, I'm going to go for the increasing one, because when we restrict our domain, there's sort of things we look for. We try and keep it in the positives if we can. We try and include 0 if we can. We try and get as close to 0 if we can't. So in that case, I'm going to go for x is greater than or equal to 0, because our parabola is always increasing for that. The range doesn't change. It still captures the whole range of the original function by doing that. So we end up with, well, let's work it out. Swap the x and the y's around. X equals y squared. Make y the subject. We get x to the power of a half, or the square root of x. Its domain is x is greater than or equal to 0. because you can't find the square root of a negative number. And the range also is y is greater than or equal to 0. And if I was to draw it, we've ended up with the top half of the parabola there on its side. Let's have a look at an HSC question. So yes, they've given us the classic bell curve, e to the power of minus x squared. So that's the graph we're playing with. The first thing they've told us is it has 2 points of inflection. Now, inflection points are where it changes concavity. So it goes from concave up to concave down and vice versa. They want us to find the x-coordinates of these points. Now, it turns out, and we'll see this later when we look at curve sketching in a bit more detail, that your possible inflection points happen when the derivative is equal to 0. Because if you think about it, if it's when concavity changes, it's like if you're moving forward and then moving backward, you must stop. It's impossible to go one way and then change direction without stopping. It might be for an instant, but you have to stop in order to change direction. So it's that sort of idea. If we want to find where it changes concavity, we want to find out when it stops or when it's equal to 0. So we're looking for second derivative is equal to 0. Differentiate it once, and I get minus 2x e to the minus x squared. To differentiate it twice, I'm going to have to use a product rule now. So write down the first, minus 2x. Diff the second, minus 2x e to the minus x squared. Plus, write down the second, e to the minus x squared. Diff the first, minus 2. That's got a common factor there of e to the minus x squared. And we're left with 4x squared minus 2 in parentheses. We want to know when that is equal to 0. Well, e to the minus x squared equals 0. That can't happen, because our exponential will never equal 0. So it must be the other bit. 4x squared minus 2 is equal to 0, which gives us x is equal to plus or minus 1 on root 2. What we'll find when we do look at curve sketching is that they're the possibilities. You then usually have to test the points. In this case I don't, because in the question it told me they have 2 points of inflection. Because I've only found 2 possibilities, well, they must be the 2. I don't need to test them. If I had come up with, say, 3 or 4 possibilities, then I would have to test them to find out, well, which one of these are the 2 that they're looking for. But in this case, I've only found 2. All right, part B. This is the bit I'm probably more interested in at this stage. Explain why it must be restricted if it's to have an inverse function. Well, that's where they're looking at that idea about, well, it needs to be 1-to-1. And our curve that they've given us is not 1-to-1. It doesn't pass, if you like, the horizontal line test. So I got a bit fancy and by using all the technical terms and said, oh, well, there must be a 1-to-1 relationship. Another way of saying it, every value in the domain must give a unique value in the range and so on. So this one doesn't satisfy it. So that's why we need to restrict it. So now they want us to find a formula. They've told us the restriction is going to be x is greater than or equal to 0. So we swap the x and the y's around, and we have to make y the subject. Well, after a bit of working out there, we get that y is plus or minus the square root of the log of 1 on x. Plus or minus. Well, we can't have plus or minus because we need to be unique. We need to know which one is it. But remember, the domain of the original function becomes the range of the inverse function. Now, the domain of the original function we restricted to x is greater than or equal to 0. Therefore, the range of my answer has to be greater than or equal to 0. So plus or minus the square root, I must have the positive square root to get answers greater than or equal to 0. So y has got to be greater than or equal to 0. There's my formula. Y equals the square root of the log of 1 on x. So then they've asked us, well, what's the domain of the inverse function? Well, the domain of the inverse function must be the range of the original function. And they gave us a picture, and it was between 0 and 1. But it didn't include 0 because there was an asymptote, remember. So again, it swaps around, so we get 0 is less than x is less than or equal to 1. And the last part of the question was to draw the curve. So we just have to reflect it in the line y equals x. I might have cheated a bit by just rotating it with a cut and paste, which of course you can't do in an exam, but essentially that's what you're doing. You're reflecting the shape in the line y equals x. Okay. So 17a we'll look at. There's a bit of a recap on inverse functions from term 1. Let's see how much we remember.